Okay, this is recording. I will make sure this gets up tonight. I will need to get rid of these. So I'm gonna get started because I want to make sure we get through everything. So the test will be on Wednesday, the 8th. I will provide constants, but for like a formula sheet, you get a sheet of paper that you can write whatever you want on as a formula sheet. Single sheet of paper, double-sided. Should be preferably handwritten. You will need a calculator. I will have calculators I can loan out. You cannot use a phone. So I'm just going to get started, and because I want to make sure we get through everything, I'll just go through and do the problems as they come up. These slides are all on Blackboard with solutions. So, start with a summary of chapter 1. Physics is based on a small number of laws and principles. The units of length are meters. The unit of mass is kilograms. The unit of time is seconds. All terms in an equation that are separated by a plus or a minus or an equal sign need to have the same dimensions. Because you can't add things with different dimensions. The result of a calculation should only have as many significant figures as the least accurate measurement used in it. You can convert one unit to another by multiplying their ratio. Order of magnitude calculations are designed to be accurate to within a power of 10. Scalars are numbers. Vectors have both a magnitude and a direction. For problem solving, the sort of problem solving procedure is read the problem, sketch the problem, visualize, strategize, identify equations, solve, check, and explore limits or the extremes. So here's some example problems. Did I not do animation? Oh, bugger. I just filled in solutions on these. Oops. I'll do the quick solution then. Oh, no. Just like the whatever. I may not have done the animations right for this, but I'll just go through problems on this solution. So to convert 305 centimeters to meters, you'll 1 centimeter, 100 centimeters equals 1 meter. So you'll divide by 100 and get 3.05 meters. To convert 25 milligrams to kilograms, 25 milligrams times 1 gram per 1,000 milligrams times 1 kilogram per 1,000 grams gives you 25 times 10 to the 6 kilograms, or 2.5 times 10 to the minus 5 kilograms, or 0.00025 kilograms. So, chapter 2 is about kinematics. Distance is the total length of travel. Displacement is the change in position. Average speed is distance over time. Average velocity is displacement over time. Instantaneous velocity is the average velocity measured over an infinitesimally small time, or really just the time derivative of displacement. So instantaneous acceleration is average acceleration measured over an infinitesimally small time. Average acceleration is change in velocity divided by change in time. So, velocity is x, minus x naught over t. Acceleration is v minus v naught over t. Deceleration is when a velocity and the acceleration have opposite signs. You get your speed decreases. Constant acceleration, the equations of motion relate position, velocity, acceleration, and time. And those equations are velocity equals initial velocity plus acceleration times time. Position is initial position plus initial velocity times time plus 1/2 acceleration times time squared. And velocity squared is initial velocity squared plus 2 times acceleration times change in position. For freely falling objects, there's a constant downward acceleration of g of 9.80 meters per second squared. So here are the equations. Average velocity is displacement over time. So, x2 minus x1 over t2 minus t1. Average velocity, velocity is the derivative of x with respect to t. Acceleration is the derivative of velocity with respect to t. And for constant acceleration, position, is x naught plus v naught t plus 1/2 acceleration times time squared. Velocity is v naught plus acceleration times time. And velocity squared equals v naught squared plus 2 times acceleration times delta x. So here, if you have a car traveling at 30 meters per second, brakes, and has an acceleration of minus 3 meters per second, how much distance does it take to come to a stop? And so velocity is initial velocity plus 2 times acceleration times delta x. So if we solve for delta x is final velocity squared minus initial velocity squared over 2 times acceleration. Our final velocity is 0. Our initial velocity is 30 meters per second. So this is the initial, the final equals 0. And our acceleration is minus 3 meters per second squared. So 30 squared is 900 divided by 2 times minus 3. So negative 900 over negative 6 gives us 150 meters. Any questions? So if you have a car traveling at 5 meters per second and it accelerates to 25 meters per second in a time of 6 seconds, what is the acceleration of the car? So for this, velocity equals initial velocity plus acceleration times time. Acceleration is velocity minus initial velocity over time. So acceleration is 25 meters per second minus 5 meters per second over 6 seconds, or 3.3 meters per second squared. Sorry. And these slides with everything worked out are all up on Blackboard. So a rock is dropped from rest at a height of 100 meters. Where is it located after 4 seconds? What is its velocity after 4 seconds? So here we're going to use the fact that G equals 9.80 meters per second squared. The constant I'll be giving you on the exam. So this is the solution. I'll walk through it. We want to find its position. Its position is its initial position plus its initial velocity times time plus 1/2 its acceleration times time squared. Its initial position is 100 meters. So for this problem, it's dropped from rest at a height of 100 meters. So x naught is 100 meters, v naught is 0 meters per second. Acceleration is negative 9.80 meters per second squared. And time is 4 seconds. We have 100 meters minus 0 times 4 seconds. Plus 0 times 4 seconds plus 1/2 times 9.80 meters per second squared times 4 seconds squared, which is 100 meters minus 78.4 meters, which is 21.6 meters. The velocity is the initial velocity plus the acceleration times time. So our initial velocity is 0. Our acceleration is negative 9.8 meters per second squared times 4 seconds. Our velocity will be negative 39.2 meters per second. And that was chapter 2. Chapter 3 is about scalars and vectors. So a scalar is a number with appropriate units, while a vector is a quantity with a magnitude and direction. A vector has components. The x component is a cosine theta. The y component is a sine theta. That's if you have some vector of length a at an angle theta. This is a cosine theta. This is a sine theta. If you know the components and want to find the magnitude, magnitude is ax squared plus ay squared, all to the 1/2 power or square rooted. And the direction, theta, is the inverse tangent of ay over ax. And if ax is negative, you have to add 100 or add or subtract 180 degrees. I don't think that actually comes up on any of the problems on the test. To add vectors graphically, you place the tail of the second at the head of the first, and the sum points from the tail of the first to the head of the last. To add them by components, you add the components. If C is A plus B, CX will be AX plus BX, CY will be AY plus BY. I mean, yeah. For component method, add the components of the individual vectors, then you can find the magnitude and direction. There are unit vectors, which are dimensionless and of unit length, and the position vector points from the origin to a location. The displacement vector points from the original position to the final position. And it is the position vector of the final position minus the position vector of the original position. The velocity vector points in the direction of motion. The acceleration vector points in the direction of change of motion. And then if you have relative motion, the velocity of 1 with respect to 3 is the velocity of 1 with respect to 2 plus the velocity of 2 with respect to 3. So here are the equations. AX is A cosine theta. AY is A sine theta. The magnitude is the square root of AX squared plus AY squared, and theta is the inverse tangent of AY over AX. Any questions? So, forgot to organize this. I'll just go through this. If you travel 15 meters north, 15 meters east, and then 10 meters west, how far are you from where you started? And if you drew a line from where you started to where you ended, what angle would it make with a line pointing east? So this is saying if north is y hat and east is x hat, what is the magnitude and direction of the sum of these three vectors? So this vector is 15 meters north, so 15 meters y hat, plus 25 meters east, so plus 25 meters x hat, and then plus 10 meters west, so minus 10 meters x hat, because west is going to be negative x hat. So that comes out to 15 meters x plus 15 meters y. So the magnitude is ax squared plus ay squared, so 15 meters squared plus 15 meters squared, take the square root. We get 21.2 meters, or 15 times the square root of 2. And the angle is the inverse tangent of ay over ax, or the inverse tangent of 15 meters over 15 meters, which comes out to 45 degrees. That was chapter 3. On to chapter 4. So the components of motion in the x and y direction can be treated independently. Why not? Plus 1 negative b squared and squared u naught y squared plus ay and 2ay delta y. In projectile motion, the acceleration is negative g in the y direction. It's downwards. If the launch angle is 0, the initial velocity will only have an x component. The path followed by a projectile is a parabola, and the range is the horizontal distance the parabola travels. So some equations. The velocity vector is the time derivative of the position vector. The average velocity is displacement over time. The acceleration vector is the time derivative of the velocity vector, or the second derivative of the position vector. Average acceleration is change in velocity over change in time. So for constant accelerations, we can write this out in vector form like this, which can be split into x and y components. X equals x naught plus vx naught t plus 1/2 acceleration x t squared. Vx equals v naught x plus ax t. Vx squared equals v naught x squared plus 2ax delta x. And the same thing with y. Y equals y naught plus v naught plus vy naught t plus 1/2 ay t squared. Vy equals vy naught plus ay t. Vy squared equals vy naught squared plus 2ay delta y. And the range equation for flat ground is that range will be the initial velocity that it's fired at over g times sine of twice the angle that it was fired at. So here, if we have a cannon with a muzzle velocity of 15 meters per second, fired horizontally off the top of a 20-meter wall, how far from the wall does the cannonball hit the ground? So what we know here, we know our, we know v naught x is 15 meters per second. V naught y is 0. Acceleration x is 0. Acceleration y is negative g. And x naught is 0, and y naught is 20 meters. And we know that the final y is 0, and we're looking for x. So what we're going to do is, because we know things about y and we want to find things about x, we will tie things together with time. So we'll start by finding the time it takes for it to hit the ground. So y equals y naught plus v naught y t plus 1/2 acceleration y times t squared. So y is going to equal y naught plus 0t minus 1/2 gt squared. So 0 equals 20 meters plus 0 minus 1/2, 9.8 meters per second squared times t squared. You solve for t, you get t is 20 meters times 2 divided by 9.8 meters per second squared. So 40 divided by 9.8. The time that comes out is 2.02 seconds. Then we can feed that into our equation for x. X is equal to x naught plus v naught xt plus 1/2 acceleration xt squared. X naught is 0. Acceleration x is 0. So both of these go away. Then we're just left with v naught, vx naught times t. So 15 meters per second times 2.02 seconds comes out to 30.3 meters. Here we have an arrow is launched at an angle of 60 degrees from the horizontal at 5 meters per second on a level plane. What angle does it impact the ground at, and how far does it travel? Well, the path of a projectile is a parabola. The angle a parabola will make with a horizontal line is the same on both sides. So the angle it's launched at will equal the angle it lands at. So the landing angle will be 60 degrees, but pointed down instead of up. So it will be negative 60 degrees by symmetry. And then the range, well, we can use the range equation. Range is speed squared, initial velocity squared over g times the sine of twice the angle. So it's fired at 5 meters per second. That's our initial velocity. Our angle was 60 degrees, so 5 meters per second squared, divided by 9.8 meters per second squared, times the sine of 2 times 60 degrees. So the sine of 120 degrees, this comes out to 2.2 meters. Questions? So, I guess I'm going a lot faster than expected. Probably because I messed up in the way the problems are presented. But I'll happily go back over anything if you have any questions when we're done. A force is a push or a pull. Mass measures the difficulty in accelerating an object. Newton's first law is if the net force on an object is zero, its velocity is constant. An inertial frame of reference is one in which the first law holds. Newton's second law is some of this. Sum of all forces on an object equals mass times the acceleration of the object. A free body diagram is a sketch showing all the forces on an object. Newton's third law is that if an object 1 exerts a force F on object 2 exerts a force minus F on object 1. So that's force on 1 from 2 equals minus force of 2 from 1. Contact forces are an action-reaction pair of forces produced by two objects in physical contact. Forces are vectors. Newton's laws can be applied to each component of the forces independently. Weight is the gravitational force exerted by the Earth on an object. On the surface of the Earth, weight equals mg. Apparent weight is the force from contact with a floor or scale. Normal force is the force exerted perpendicular to a surface by that force. The normal force will be big enough, will be whatever it needs to be to keep the object from passing through the surface. So it'll always be pointing out of the surface, pushing away from the surface, and it will change its size as needed, depending on how much the object is pushing into the surface. So it can be equal to, lesser than, or greater than the object's weight. Because if you have an object that you're pushing down on, the normal force will have to be bigger. If you're somehow lifting it up a little, the normal force will be less. So the equations, force F equals ma, and force 1, 2 equals minus force 2, 1. And weight equals mg. So 4 kilogram mass has 3 forces on it. Force 1 is 35 newtons. Force 2 is 55 newtons. Force 3 is minus 15. Force 1 is 35 newtons in the x direction. Force 2 is 55 newtons in the y direction. And force 3 is minus 15 newtons in the x direction and plus 25 newtons in the y direction. What is the acceleration of the mass? Well, force equals mass over acceleration. Acceleration is force, sum of all the forces over mass. The force 1 plus force 2 plus force 3 over mass. The 35 newtons in the x direction plus 55 newtons in the y direction plus negative 15 newtons x, 25 newtons y, all divided by 4 kilograms. So 35 newtons minus 15 newtons is 20 newtons, and 55 newtons plus 25 newtons is 80 newtons. So the net force is 20 newtons in the x direction and 80 newtons in the y direction. And we divide that by 4 kilograms, and we get 5 meters per second in the x, 5 meters per second squared in the x direction, and 20 meters per second squared in the y direction. Here we have a mass on a slope. Here it is easier to set up the coordinate system to match the slope and not gravity. We have a 2 kilogram mass that slides down a slope of 30 degrees from the horizontal. What is the force on the slope from the mass? Well, we can look, the force is in the x direction. That's mg sine theta from the component of mg, gravity pulling down the slope. And the forces in the y direction equals 0, because it is neither going into or out of the slope. And that is the normal force minus mg cosine theta. So for this, we've broken mg into mg sine theta and mg cosine theta, because this angle is theta, the same as the angle of the slope. So the normal force ends up equaling mg cosine theta. The normal force is mg cosine theta times y. The force of the slope on the mass is minus the force of the mass on the slope. So the force of the slope on the mass is minus normal force. So that's going to be the force of the slope on the slope from the mass is minus mg cosine theta y. The force on the slope from the mass is minus 2 kilograms times 9.8 meters per second squared times the cosine of 30 degrees times y hat. So that comes out to minus 17 newtons. So 17 newtons into the surface, into the slope. And it has no force horizontal because it's frictionless. Here we have a 3 kilogram mass that pushes on a 4 kilogram mass. So causing it to accelerate at 1.5 meters per second squared. What is the acceleration of the 3 kilogram mass? So the 3 kilogram mass is applying, oh, this isn't, sorry. It's like some spring, so I should remember apart or something. So the force on 3 from 4 is equal to minus the force on 4 from 3. So mass 3 times acceleration 3 equals minus mass 4 times acceleration 4. So acceleration 3 is minus mass 4, acceleration 4 over mass 3. So acceleration 3 is 4 kilograms times plus 1.5 meters per second squared divided by 3 kilograms minus So that's 6 divided by 3, but minus, so minus 2 meters per second squared. So, chapter 6. Friction is due to microscopic roughness. For kinetic friction, the force for kinetic friction. Let's see. Friction kinetic. I will just erase the in here. Is mu kinetic times the normal force. For static friction, the maximum for static is mu static times the normal force. Friction, kinetic friction opposite the direction of sliding. So kinetic friction is going to act generally opposite the velocity. Static friction acts to keep the surfaces not moving relative to each other. Tension is the force transmitted through a string. You go around a pulley that just redirects tension. For an ideal spring, force of the spring is minus kx. The minus sign is there because the force points opposite the displacement. You pull a string one way, the force is going to push in the opposite direction. An object is in translational equilibrium if the net force acting on it is 0. That happens if it's not moving. Connected objects have the same acceleration. The force required to move an object of mass m in a circle of radius r is mass times acceleration centripetal, which is mass times velocity squared over radius. So kinetic friction is mu kinetic times normal force. Static friction, the maximum is mu static times normal force. An ideal spring, the force is minus kx. And for centripetal force, that's mass times acceleration centripetal, which is mass times velocity squared over radius. So if a 5-kilogram block slides down a 30-degree incline with an acceleration of 1 meter per second squared, what is the coefficient of kinetic friction between the block and the incline? So here, we need to figure out what the friction force is in order to find the coefficient of friction. And to figure that out, we need to know the force in the x direction and the normal force. So we'll do both of those. The normal force is the easier one to find because the force is in the y direction equals 0. The normal force equals minus mg cosine theta. The normal force equals mg cosine theta. Because again, component of mg in the y direction is going to be cosine theta. For x, we have mg sine theta going down the slope. So in the y direction, we have mg cosine and this direction with mg sine theta. Minus the friction force, and that equals mass times acceleration. Kinetic friction is mu kinetic times the normal force. So mg sine theta minus mu kinetic times the normal force equals mass times acceleration. We want to solve for mu kinetic. We get mu kinetic times the normal force is mg sine theta minus mass times acceleration. We can plug in our value for the normal force of mg cosine theta. Mu kinetic is mg cosine theta. Mu kinetic times mg cosine theta equals mg sine theta minus mass times acceleration. We can divide both sides by mg cosine theta and get mu kinetic is mg sine theta minus mass times acceleration over mg cosine theta. There is a nice factor in here. We could plug in the numbers at this point. We know all these values, but it turns out mass cancels. So mu kinetic is g sine theta minus acceleration over g cosine theta. So mu kinetic equals 9.8 meters per second squared times the sine of 30 degrees minus 1 meter per second squared over 9.8 meters per second squared times the cosine of 30 degrees. And that comes out to 0.46. Kind of complicated problem. Do you have any questions about it? Here we have two masses connected by a rope, as shown below. If mass 1 is 10 kilograms and mass 2 is 5 kilograms and the table is frictionless, what is the acceleration of the masses? So I believe I put the solutions on the next slide. Yeah. So here, we can treat these two connected objects as a single system with an acceleration and some forces on it. The net force on all the masses equals the total mass times the acceleration. Mass 1, the net force. So we'll ignore the tension in the string, basically. Mass 1, the forces in the y direction cancel out. Mass 2, there's no forces in the y direction, but the force in the x direction is the weight of mass 2. So we get weight 2, that's the net force on this system, equals mass 1 plus mass 2 times acceleration. Weight 2 is m2 times g. That's mass 1 plus mass 2 times acceleration. So acceleration ends up equaling mass 2g over mass 1 plus mass 2. Or 5 kilograms times 9.8 meters per second squared divided by 10 kilograms plus 5 kilograms. So 5 kilograms over 15 kilograms times 9.8, which is 3.27 meters per second squared. You could also get this by putting together the system of equations where tension equals mass 1 times acceleration, and weight 2 minus tension equals mass 2 times acceleration. And if you add these equations together, you get weight 2 equals mass 1 plus mass 2 times acceleration. That equation. So you could treat them as a system, or you can write a system of equations and solve the system of equations for acceleration. Both are viable. We got this? You have a 0.25 kilogram mass hanging on a spring, stretches it by 1 centimeter. What is the spring constant of this spring? Well, force on a spring, oops, I hit the wrong button. Force on a spring is minus kx. So we want to find k. So k is going to be minus the force on the spring over x. So that's minus mg over x. So minus 2.5 kilograms times 9.8 meters per second squared over minus 0.01 meters. You need the extra minus sign in there somewhere to make sure you get a positive number for k. Force constant will always be a positive number. But the idea is that the force, the sign of the force and the sign of the displacement will always be different. One will be positive and the other will be negative. So K comes out to 2,450 newtons per meter. Here we have a car traveling in a circle, a roller coaster car traveling in a circle. What is the force from the track on a 1,000-kilogram roller coaster car traveling at 10 meters per second at the top of a 10-meter radius loop? Well, we know the net force on the car is the centripetal force because it's going around in a circular loop. And the forces on that car are mg, the weight, and the normal force of the track, both pushing down. So weight plus normal force equals centripetal force. So mg plus normal force equals mass times speed squared over radius. So the normal force, which is going to be the force from the track, is mass times speed squared over radius minus mg. So now we can plug in our numbers. 1,000 kilograms times 10 meters per second squared over a radius of 10 meters minus 1,000 kilograms times 9.8 meters per second squared. That's 10,000 newtons minus 9,800 newtons, which comes out to 200 newtons. So I chose numbers where almost all the force is coming from gravity. Here we have a static equilibrium problem. We have a 2-kilogram mass hung from a string that harms an angle of 45 degrees to the horizontal at both ends. And we want to find the tension in the string. So both of these are at 45 degrees. Forms this angle theta up here, so it'll be the same angle theta down here. And we'll get, if we look at the forces in the x direction, we have tension cosine theta in the positive x direction and tension cosine theta in the negative direction, and that equals 0. If you wanted to, you could set this to be tension 1 and tension 2, but it's not that hard to figure out that this lets you know that tension 1 equals tension 2. So this is tension 1, this is tension 2. So if this was tension 1 and this is tension 2, we find that tension 1 equals tension 2. So we can just use tension for both of these for y. Then in the vertical direction, we have tension sine theta from T1, tension sine theta from T2, and minus mg. And that also adds up to 0, because again, nothing is moving. So 2t sine theta equals minus mg equals 0. 2t sine theta equals mg. Tension equals mg over 2 sine theta. Tension equals 2 kilograms. So it's 9.8 meters per second squared over 2 sine of 45 degrees. So tension ends up equaling 13.9 newtons. And that is the review. So that went really quickly. Is there anything you guys have any questions about? Anything you are confused about and you'd like me to go over? Otherwise, I'll see you on Wednesday for the exam. The exam will have 10 problems, each worth 10 points. You'll get partial credit. So make sure to show your work. Because if you make like a small mistake, I'll give you partial credit. But if you make, I'll definitely, I give credit for trying. So try every problem. Yeah. So I'll see you on Wednesday.
So for the front sheet, is it like basically printer paper?
Yeah, just anything about normal letter size. You can use both sides. And you could use a sheet from your notebook, that would be fine. That's about the right size. I'm just saying, you know, I don't want you to come in with like a sheet that's the size of this table. Or something. I'm just stating roughly letter size.
There's some showdown with the I couldn't relocate on the computer, for the access code, and I wanna just make sure I'm caught up on your class.
Okay,
I
let
think
me-
Your class is the only class I don't have my homework done for, because I just have not been in your peers.
Let me end this meeting.